Let's go ahead and get started.
Mhm.
Okay. All right. Welcome, everybody, to our first Frontiers event. Thank you so much for making it out. Um, as I just said, this is our first Frontiers talk. It's a new series that we're doing where we bring top researchers, engineers, designers, leaders working at the cutting edge to go deep on their research. And so today's speaker is Helen Lu. She's a PhD student at Tufts, and she's working on neuro-symbolic AI and human-in-the-loop machine learning. Without further ado, Helen, thank you very much. Take it away.
Hi, everyone. This is Helen. So today I will be presenting novelty adaptation through hybrid LLM symbolic planning and LLM guided exploration. So a little bit about me. I previously graduated from University of Berkeley with a bachelor in psychology, and I was working as a research scientist at Georgia Tech. I'm currently doing a PhD in human-robot interaction at Tufts University at the Human Robot Interaction Lab. So if any of you are interested in human robot interaction, I would be glad to chat about this topic and also about neurosymbolic AI in general. So there is a lot going on in the title, so let's break it down. First, let's consider what planning is in the robot and what we need a large language model for in planning and why that helps novelty adaptation. So to understand this, let's consider a scenario in which a robot arm is being programmed to prepare coffee. The goal is for the robot to place a mug under the coffee pot dispenser, pick up a coffee pot from the tabletop, and insert it into the coffee pot holder and close the lid on the coffee pot holder. So the question is how we can enable the robot to do this. Enters me, the human software engineer. I probably spent a couple hours to define a few detectors. So these are detectors and operators for the robot. The detectors enable the robot to basically detect the environment's current state, what's going on, what's true, what's not true about the current state. So for example, here we have a holding detector, and it takes as parameters an object and the gripper, and it returns is whether the gripper is holding the object or not. And we have an open detector, and it takes as a parameter a container, and it tells the robot whether the container is open or not. And we have a free detector that only applies to a gripper object. And it basically tells the robot whether the robot arm's gripper is free. We also have an in detector that basically tells a given an object and a container whether the object is in the container. So as you can see with detectors like these, the robot is able to detect basically what each object's state is. So the operators, on the other hand, we have an open holder operator, and it takes as parameters a holder, a gripper, and it's defined with a set of preconditions and a set of effects. So the precondition here is basically saying when the holder is open, which this information is can be given by the holding detector. When the holder is open and the gripper is free, the effect after executing this open holder operator is the holder will become open from being not open to open. And the close holder detector similarly says if the holder is open and the gripper is free, after executing this operator, the holder will be not open. And similarly, we have a pickup from tabletop operator and a place pod in holder operator. So what this enables the robot to do is generate plans for reaching goals. So given a goal state, which is make coffee, the robot is able to then observe the current state, reason about the operators that need to be applied, and come up with a sequence of operators that would lead from the current state to the goal state. So in this case, the person says, please make me some coffee. And the robot is able to reason through the operators, the preconditions, the effects, and come up with a sequence of executing these operators that would lead from whatever the current state is to the goal state. In this case, the sequence is first I pick up from the tabletop the mug. I place the mug under the holder. I open the holder. I pick up from tabletop the coffee pod, and then I place that pod in the holder. And finally, I close the holder. So at the core of symbolic planning is really just search. Given a goal state, which is this state, the robot detects what the current state is. The current state checks which operators are applicable, meaning their preconditions are satisfied. So these three operators are applicable. By the way, do you guys see my cursor, my mouse? Because I'm pointing to things.
Yes.
Okay, perfect.
Yep.
Checks what the resulting states are, what the resulting states would be after applying those hypothetical executable operators. Repeats the process, grows a search tree until it finds the path that basically goes from the current state to the goal state. And you can apply any of your favorite search algorithms, such as breadth first search, depth first search here. The good thing is symbolic planning handles well long horizon tasks. It doesn't matter how many operations a task requires, as long as there is a solution, the robot will be able to find it after searching for it, maybe for a long time. The bad thing is, this is a very rigid approach that operates under heavy assumptions. One assumption is that the environment is perfectly controlled and modeled by the robot's knowledge of how the world state is going to change after applying each operator. It's also assumed that this model, the human engineer has given the robot is sufficient to find plans in any situation the robot might come across. And needless to say, a lot of things could go wrong, and this approach stops working when there is a novelty of any kind. So one such novelty is novel objects that require new operators to manipulate. To use our original coffee preparation task as an example, the robot goes, I got this, to clueless in no time after we introduce an everyday object such as a drawer into the environment and start the coffee pot as being inside the drawer as opposed to just on the top, the tabletop. And this is because the robot's knowledge base does not come equipped with an operator that can transform the state of the world from the coffee pot being inside the drawer to the coffee pot being outside the drawer. Because me, as a human software engineer, didn't foresee that the coffee pot would ever be inside the drawer, because it's quite impossible for the human to foresee all kinds of situations that the robot might be in. So the result is that the robot fails to find the plan after searching in its knowledge base. And then what we can do in this case is add more work for the human engineer. Tell her to add the missing operators to the robot's knowledge base to actually enable the robot to then interact with the drawer object. In this case, we add the open drawer operator and the pickup from drawer operator. These two operators would enable the robot to then open the drawer and pick up the coffee pot from inside the drawer. So that's one option. Obviously, this is not a long-term solution, though. As you can see, every time the robot encounters a novel object, the engineer is going to have more work to do. And the engineer works around the clock every day just to help the robot adapt to novel objects it encounters. I guess this is great job security for the engineer, but maybe it does not offer the greatest job satisfaction, as there are probably better ways of making the robot do this. So what if we replace the human engineer here with a large language model, such as GPT-4o, so the human engineer can go on vacation? The idea here is that since the large language model has been trained on internet scale data, and shows the emergent capability of common sense reasoning. We can leverage it as a knowledge source, and specifically when encountering a novel everyday object that requires just common sense operators to manipulate. The large language model should be able to then tell the robot what the missing operators are. And currently we are building a hybrid large language model symbolic planning architecture that integrates large language model into the planning process. When a traditional symbolic planner fails to find a plan due to missing operators regarding a novel object added to the environment, so a hybrid planner is able to leverage the vast common sense knowledge encoded in the large language model to then fill in the gaps in the robot's current knowledge base. And to just recap what we have done so far, we start with a coffee making robot with a knowledge base of operators, a traditional symbolic planner, and the controllers that have been implemented by a human engineer that have been made sure to work in a starting coffee making domain. We introduce a novel object with only a traditional symbolic planner. And it's the robot's original knowledge base. The robot just lacks the necessary knowledge to generate a plan to complete the coffee making task. We integrate then a large language model into the robot's planner. The large language model generates new operators for interacting with the novel object by completing a series of reasoning tasks. Effectively, what we have done is extracted common sense knowledge out of the large language model in a structured format that is consistent with and works with the existing structured knowledge in the robot's symbolic knowledge base. So it turns out actually that prompting the large language model to directly come up with a well-defined structured operator in a given current search state is actually too complicated of a reasoning task. And as research shows, large language models are not nearly perfect when it comes to reasoning tasks. So what we do is we break the operator definition task down into 3 subtasks. The first one being define the name and parameter objects for this operator. The second one being define the preconditions that must be met in the current search state for the operator to be executable. The last one being define the effect as a result of executing this operator. And we use 2 prompting techniques to further enhance the large language model's performance on these reasoning tasks. One is zero-shot chain of thought prompting, and the other one is self-consistency. So a little bit about chain of thought prompting. This is a popular prompting technique to elicit reasoning. So here, this is an example of a math, I think, question answering. So with standard prompting, you ask the model, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And then you show it one example is saying the answer is 11. And then you ask the large language model. The cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they now have? The model gives you something like 27, which is wrong. With chain of thought prompting, what you do is you not only demonstrate what the answer is, you also demonstrate the reasoning process. So the same tennis ball question. And then in addition to the answer being 11, you also include in your prompt this reasoning process that says, Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls. So 5 plus 6 equals 11, and that's how I arrived at the answer being 11. So now what you get is the model will try to emulate your reasoning process before coming up with an answer for this question, the real question you actually want the model to answer. So the model says, okay, following this reasoning process, the cafeteria had 23 apples originally. 1 second, let me move this out of it. They used 20 to make lunch. So they had 23 minus 20 equals 3. They bought 6 more apples. So they have 3 plus 6 equals 9. The answer is 9. So this is what basically chain of thought prompting is you prompt the model to include a chain of thought in before it tries to give you an answer. And that's shown to increase the model's performance on reasoning heavy tasks quite a bit. And what a few short chain of thought is what I basically just showed. You include question answer pair examples, and you include a few of them in your prompt before asking the model the real question that you wanted to answer. What zero shot chain of thought is basically some researchers have found that instead of including this whole chain of thought example, you can just basically add this one sentence. Let's think step by step. And what this does is it actually elicits similar reasoning process, like a reasoning output from the model, and the performance is actually comparable. So a little bit about self-consistency as well. This is also a prompting technique, and it involves generating multiple responses to the same prompt and selecting the most frequent output. And the assumption here is the most frequent answer is also the most correct one. So basically, when you prompt a large language model, you prompt it 5 times, you might get 2 different answers. You may get 3 times one answer and 2 times another answer. And what you do in this case is you say, okay, the most frequent answer is probably the correct answer. So here they are showing that this is the chain of thought prompting technique that I just showed, and self-consistency actually also further improves the model's performance on reasoning tasks on top of chain of thought prompting. So with self-consistency, what you do is you let the language model go through a diverse set of reasoning paths. So here is one reasoning path, and the answer to this question about how many duck eggs is 18. And here is another reasoning path, and the answer the model arrived at is 26. And then finally, here is another reasoning path, and the answer is again 18. So after counting all of the different answers you get, you say, okay, seems like 18 is the majority answer, so 18 is the answer that we are going to go with. So what we did in our research is we also integrated chain of thought, zero-shot chain of thought prompting and self-consistency into our hybrid LLM symbolic AI planner. And here, this is a case where if you just straight up prompt the large language model to generate a new operator, it actually doesn't do the job, it actually fails. So what happened here is the large language model is prompted in this state to propose a new operator, and it proposed the open drawer operator. And the effect of the open drawer operator, it says, is the drawer will become open and the coffee pot will still be inside the drawer, and the gripper will no longer be free because presumably the gripper will be gripping the drawer. So in this state, I prompted again to say that, okay, propose another operator for interacting with the drawer. Now that it's open, can you think of what I can do next? And it's saying, oh, you can take the pot from the drawer, but the precondition for this operator, it says it's the gripper has to be free, which is not satisfied in this current state. So the large language model has made a mistake here. So what we do to mitigate mistakes like this is we added this chain of thought zero-shot prompt, this sentence here, let's think step by step. And we also sample 3, I mean, it's a hyperparameter that you can set, but typically we sample 3 to 5 answers, outputs from the large language model, and we take the majority answer. Here, this is the wrong answer, and these 2 are the correct answers. So after we have defined the missing operator, we still have to learn it. It's one thing in robotics to know what the missing operator is. It's another thing to actually be able to perform the missing operator. In other words, it's one thing for the robot to add to its knowledge base and open drawer operator, but it's another thing for the robot to actually be able to then reach forward, grab the handle of the drawer, and pull it in the right direction, resulting in the drawer actually being open in simulation or in the real world. So much of the planned next phase of this work is a work in progress, ongoing work. So much of the planned next phase for this project is on how to enable the robot to actually perform the missing operator once the LLM has defined them in a structured manner. So there are 3 options that I am currently considering. The robot can learn the missing operator from using reinforcement learning. The robot can learn the operator by asking a human for a few demonstrations and try to copy the human. Or we can even use demonstration to fine-tune a vision language action model. And for reinforcement learning in particular, I like to think of reinforcement learning as a form of learning from exploration and also a form of search, really. So robot with reinforcement learning, what happens basically is a robot starts by trying random actions. So it tries random actions in the environment, in the world, and detects how the environment state changes with each action. A robot arm typically has 6 to 7 joints, and these actions are typically just like defined as rotating each joint in a random direction for a random small degree, and randomly changing the gripper opening aperture. Occasionally, the robot will have tried an action that results in a favorable state change. In the open drawer case, the robot might, after trying many actions randomly, try one action that results in the drawer being open. So the robot gets a reward whenever a favorable state change happens. Over time, the robot learns what the most favorable action is in each environment state. So this is one option. Or another option, we can ask a human engineer to come back early from vacation and provide demonstrations for the robot. So say the robot has structurally defined the open drawer is the missing operator that I need to learn. And these are the preconditions and these are the effects. And you can communicate to a human demonstrator. I need to learn how to open drawer, and I'm in the state where all the preconditions are satisfied. Can you then teleoperate me typically to get to a state where the drawer is open? So what a demonstration is essentially a sequence of recorded robot actions that the robot took and the state changes under the human's teleoperation. The robot can learn to copy them or through imitation learning. So that's another option. Alternatively, we can also use these demonstrations to fine-tune a vision language action model. But regardless of which of the 3 options we choose to go with to fill the gap in the robot's knowledge, we still need to answer the question of how to identify and structurally define the gap in the robot's knowledge in a way such that it fits with the existing knowledge structure and can thereby work with its existing reasoning system, such as a symbolic planner. And that's what the hybrid LLM symbolic planner is doing. So there are some existing planning and learning approaches. And these existing approaches typically require a lot of explorations by the reinforcement learning agent. So what these approaches do is the RL agent is spawned here when in the current state. Whenever the robot says, okay, using the existing knowledge in my symbolic knowledge base, I cannot find a plan from the current state to the goal state. So I don't know what to do here. An RL agent is typically spawned just at this current state, and it goes through lots of trial and error random actions to land in a plannable state. So this kind of goes in the reverse direction. A plannable state, all of these are plannable states. A plannable state is defined as a state from which you can reach the goal state. So basically you do the search backwards. You start the search at the goal and you cache some plannable state from which you can reach the goal and use start an exploration reinforcement learning agent trying random actions in the current state. And you hope that after trying many random directions, the agent lands in a plannable state. So you can say, okay, this is what I'm missing, this operator from current state to this plannable state is what I need to really learn, because this is what can fill in the gap in my planning knowledge base. So these approaches typically require many explorations by the RL agent. So in this case, for example, the RL agent has to explore until it reaches this state, which is basically after it's opened the holder, opened the drawer, picked up the pod from drawer, and it's right now holding the pod in its gripper, is a plannable state from where it can then plan to get to the goal state. It can just, because from that state, it can then place the pod in the holder and close the holder. So the advantage with using a hybrid symbolic LLM planner is then it's able to directly fill these gaps and tell you, this is your plan. And you already know how to execute open holder. It's already in your existing operator. So you can already execute this and get here. Now you just have to spawn an RL agent that goes from this state and gets you to the open drawer effect state. And once you have done that, then you can execute this operator, and spawn another RL agent here and explore from this state to the picked up pod from drawer state. So what this enables us to do is incrementally learn these missing operators, as opposed to exploration from the very start that could take forever. So this is basically what we have done and what we still plan to do. And this is one of my work in progress ongoing research projects. And I would love to, if you guys have questions, I would love to answer them. And if you guys are also interested in this area, have done research in this area, I also would love to hear more about them and would love to chat in general.
Thank you, Helen, for this excellent talk. We can now open the floor up for questions. Okay, great. And Helen, if there are no questions, then how can people contact you or learn more about this work?
Oh yeah, so I'm on Discord, the Manifold Community Discord. I'm in the Metacognition for Robots channel, also on Discord in general. I can also leave my email and also Discord, LinkedIn in the chat if that works.
Yep, it seems like Hirsch is saying share email contact in the chat, or I think that would be good. Yeah, I think that would be a good idea. Perfect. Okay, great. Helen, thank you once again. Applause probably won't carry over well on this medium, but you deserve it. Thank you. And thank you all for attending this first Frontiers event. I would say that it was quite successful. A recording will be available. We'll post that to our YouTube channel as soon as we download it and clean it up, and we'll put it up. And then the link for that will be shared in the Discord, as well as any other notes or related materials. Once again, guys, thank you so much. If you want to attend more talks like these, make sure you subscribe to our Luma calendar, and you'll get updates and notifications on new events, including our upcoming community research call, which is another event that's coming up very soon. So, okay, thanks, everyone. Thank you, Helen.
Thank you, guys.